The life cycle of a stellar mass black hole. Every black hole has a story, a beginning, a middle, and, according to our best theories, an end. For stellar mass black holes, that story begins not with darkness, but with light. With a massive star burning bright, fusing elements in its core, holding itself up against its own crushing gravity. It's a story that spans from nuclear fires to catastrophic collapse, from violent birth to quiet, almost eternal existence, and ultimately to a final evaporation through quantum processes so slow they defy imagination. Today, we're following the complete life cycle of a stellar mass black hole, from the star that creates it, through its formation in one of the universe's most violent events, across billions or trillions of years of growth and interaction, to its eventual fate in a universe grown cold and dark. This is the biography of a black hole, from first light to last whisper. Stage 1. The progenitor star. Every stellar mass black hole begins as a star, but not just any star, a massive star, at least 20 to 25 times more massive than our Sun. These massive stars are rare. For every star massive enough to become a black hole, there are thousands of smaller stars like our Sun. But what massive stars lack in numbers, they make up for in impact. Let's follow one such star from its birth. The story begins in a giant molecular cloud, a vast region of cold gas and dust spanning hundreds of light years. Density fluctuations within the cloud cause certain regions to collapse under their own gravity. As the cloud collapses, it fragments into smaller clumps, each destined to become a star. Our progenitor star forms from one of the most massive clumps. As gas falls inward, gravitational potential energy converts to heat. The core temperature rises. When it reaches about 10 million degrees Celsius, hydrogen fusion ignites. The star is born. Massive stars burn hot and bright. A star 25 times more massive than the Sun might have a surface temperature of 30,000 degrees, 5 times hotter than the Sun, and shine with the light of 100,000 suns. It's a brilliant blue-white beacon, visible across vast distances. But this brilliance comes at a cost. The more massive a star, the faster it burns through its fuel. Our Sun will shine for about 10 billion years. A 25 solar mass star exhausts its hydrogen in just a few million years. As hydrogen in the core depletes, the core contracts and heats up. Eventually, it becomes hot enough to fuse helium into carbon and oxygen. The star enters a new phase, swelling into a supergiant with a radius potentially hundreds of times larger than the Sun. The fusion continues through successive stages. After helium comes carbon fusion, then neon, then oxygen, then silicon. Each stage produces heavier elements and releases less energy per fusion reaction. Each stage lasts for a shorter time than the one before. The silicon burning phase, the final stage, lasts only days. The star's core becomes an onion-like structure with shells of different elements, iron and nickel at the center, surrounded by shells of silicon, oxygen, neon, carbon, helium, and finally hydrogen at the surface. And then comes disaster. Iron is the end of the line. Fusing iron requires energy rather than releasing it. When the core has converted enough of its mass to iron, fusion stops. There's no more energy production to support the star against gravity. The core, now composed primarily of iron, has a mass of about 1.5 solar masses, compressed into a sphere roughly the size of Earth. It's supported against collapse primarily by electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, which prevents electrons from occupying the same quantum state. But there's a limit to how much mass electron degeneracy pressure can support. This limit, the Chandrasekhar limit, is approximately 1.4 solar masses. When the iron core exceeds this limit, collapse is inevitable. Stage 2. Core collapse and supernova. The collapse happens suddenly. In less than a second, the core implodes. As the core collapses, density and temperature skyrocket. At a density of about 10 to the 14 grams per cubic centimeter, nuclear density, the collapse is halted by nuclear forces. The core becomes essentially a giant atomic nucleus, a proto-neutron star. But the infalling material doesn't stop immediately. It continues to rain down on the proto-neutron star, bouncing off the stiff nuclear matter. This bounce launches a shock wave outward through the star. Initially, the shock wave carries enormous energy, but as it plows through the dense stellar material, it loses energy to photodissociation, the breaking apart of heavy nuclei into protons and neutrons, and to neutrino emission. Within milliseconds, the shock stalls. Here's where things get complicated and where astrophysicists are still working to understand all the details. The proto-neutron star at the core is incredibly hot, hundreds of billions of degrees. It radiates vast numbers of neutrinos, carrying away energy from the core. Normally, neutrinos pass through matter almost without interaction, but the density is so extreme that a small fraction of neutrinos get absorbed by the material behind the stalled shock, depositing energy and helping to revive the shock. The exact mechanism, whether it's purely neutrino-driven or whether instabilities like convection and the standing accretion shock instability, SASI, play crucial roles, is still being studied through detailed computer simulations. But somehow, within a few hundred milliseconds, the shock is revived. The shock wave races outward through the star, heating material to billions of degrees and triggering explosive nuclear fusion. Elements heavier than iron, including gold, platinum, and uranium, are synthesized in this cosmic furnace. After a few hours, the shock reaches the star's surface and erupts into space. From outside, we see a supernova, a stellar explosion that can briefly outshine an entire galaxy. The supernova ejects most of the star's mass into space at speeds of tens of thousands of kilometers per second, seeding the interstellar medium with heavy elements. We and everything around us are made from atoms forged in stars and dispersed by supernovae. But at the center, something remains, the collapsed core. Stage 3, the moment of formation. Whether the collapsed core becomes a neutron star or a black hole depends primarily on its mass. The dividing line, the maximum mass a neutron star can sustain, is somewhere between 2 and 3 solar masses, though the exact value depends on the poorly understood equation of state of nuclear matter at extreme densities. Let's call it 2.5 solar masses for our purposes. If the proto-neutron star has a mass below this limit, neutron degeneracy pressure, the quantum mechanical pressure arising from the Pauli exclusion principle applied to neutrons, can support it. It becomes a neutron star, a city-sized ball of neutrons with a mass greater than the sun, spinning rapidly and potentially beaming radiation as a pulsar. But if the core mass exceeds the limit, nothing can stop the collapse. Neutron degeneracy pressure is insufficient. There's no known mechanism that can provide enough pressure to halt the implosion. The core continues to collapse. Within milliseconds, it shrinks past its Schwarzschild radius. An event horizon forms. Causally, the core is now disconnected from the outside universe. Whatever happens inside cannot influence what happens outside. A stellar mass black hole is born. The typical mass of a black hole formed through core collapse is between about 5 and 15 solar masses, though the theoretical range extends from perhaps 3 solar masses up to 50 or even 100 solar masses for the most massive progenitor stars. There's actually a potential gap in black hole masses. For certain progenitor star masses, roughly 140 to 260 solar masses, the core becomes so hot during oxygen burning that photodisintegration and pair production destabilize the star, leading to a pair instability supernova. These explosions are so energetic they completely destroy the star, leaving no remnant at all. This creates a theoretical mass gap where black holes shouldn't form.
Observations from gravitational wave detections have found black holes in unexpected mass ranges, raising questions about formation mechanisms and whether the mass gap is as clean as theory predicts. But that's an ongoing area of research. For our black hole, formed from a 25 solar mass star, let's say it emerges with 10 solar masses. The rest of the star's mass was either blown away in the supernova or converted to neutrino energy during collapse. The newly formed black hole has an event horizon radius of about 30 kilometers, roughly the size of a large city. It's rapidly spinning, inheriting angular momentum from the collapsing core, and it's surrounded by debris, the fallback material that didn't escape in the supernova, but instead fell back on the black hole in the seconds and minutes after formation.
Stage 4. Early evolution and accretion. In the immediate aftermath of formation, the black hole accretes material from its surroundings. The supernova hasn't dispersed all the stellar material instantaneously. Some material falls back onto the black hole. This fallback accretion can continue for hours, days, or even years after the initial collapse, adding mass to the black hole. If the progenitor star was part of a binary system orbiting another star, the companion star might also provide material. If the companion is close enough, gas from its outer layers can be gravitationally pulled toward the black hole, forming an accretion disk. Material in an accretion disk doesn't fall directly into the black hole. It spirals inward, gradually losing angular momentum through friction and viscous forces. As it spirals inward, gravitational potential energy converts to heat. The inner regions of the disk, closest to the black hole, become extremely hot, millions of degrees, and emit X-rays. This makes accreting black holes in binary systems detectable as X-ray sources. Cygnus X1, discovered in 1964 and later confirmed to contain a black hole, is a famous example. The black hole orbits a blue supergiant star every 5.6 days, accreting material from its companion and shining brightly in X-rays. Accretion onto stellar mass black holes can be dramatic. In some systems, accretion is unstable, leading to outbursts where the X-ray brightness increases by factors of thousands or millions. These X-ray transients, or X-ray novae, flare up suddenly when accretion increases, then fade back to quiescence when the accretion rate drops. The black hole can also launch jets, narrow beams of particles and energy that shoot out perpendicular to the accretion disk at speeds approaching the speed of light. These jets are powered by the energy of the accretion flow and potentially by the rotational energy of the spinning black hole through the Blandford-Zainic process. Through accretion, the black hole grows. The growth rate depends on how much material is available and how efficiently it can accrete. In a close binary system with active mass transfer, a black hole might gain a significant fraction of a solar mass over millions of years. But for most black holes, especially those not in binary systems, accretion is limited. Once the initial fallback material is consumed and any nearby companion stars are exhausted, the black hole enters a quieter phase. Stage 5. The Long Middle Age. After the dramatic first million years, a typical stellar mass black hole settles into a long, relatively uneventful existence. If the black hole is isolated, not part of a binary system, it moves through the galaxy like any other massive object, following an orbit around the galactic center. Its gravitational influence is no different than if that same mass were in a star. Contrary to popular misconception, black holes don't suck any more than stars of equivalent mass. Occasionally, the black hole might pass near a star cluster or dense molecular cloud, accreting small amounts of gas, but the efficiency is low. The black hole's cross-section for capturing material is small, only a few hundred kilometers for a stellar mass black hole, and the interstellar medium is extremely tenuous. If the black hole is in a binary system, its evolution depends on the companion. If the companion is a main sequence star, still burning hydrogen, the system can remain stable for millions or billions of years. Eventually, the companion will evolve, possibly transferring mass to the black hole when it swells into a giant. In some cases, the companion star is massive enough to also undergo core collapse, forming a second black hole or neutron star. The system then becomes a double compact object binary, two black holes or a black hole and neutron star orbiting each other. These binary systems are special because they're destined to merge. The orbit gradually decays due to gravitational wave emission. The orbiting masses create ripples in space-time that carry away energy. This process is extremely slow initially. For a wide binary, orbital decay takes billions of years. But as the orbit shrinks, the orbital period decreases and gravitational wave emission increases. The process accelerates. Eventually, the two objects spiral together in a final plunge lasting just seconds or minutes, merging in a violent collision that releases enormous energy in gravitational waves. We've now detected dozens of these mergers through gravitational wave observatories like LIGO and Virgo. The first detection, GW 150914 in 2015, involved two black holes of 36 and 29 solar masses merging to form a 62 solar mass black hole. 3 solar masses, equivalent to the energy of the sun's entire mass, were radiated away as gravitational waves. Each merger creates a more massive black hole with its own continued evolution. In this way, stellar mass black holes can grow beyond the masses possible from single star collapse, potentially reaching 100 solar masses or more through successive mergers. Stage 6. Tidal disruption events. Occasionally, during its long lifetime, a black hole might have a close encounter with a star. If a star passes too close to a black hole, tidal forces, the difference in gravitational pull across the star, can exceed the star's self-gravity. The star is torn apart in what's called a tidal disruption event. The tidal radius, the distance at which tidal forces overcome self-gravity, depends on both the black hole's mass and the star's structure. For a stellar mass black hole and a sun-like star, the tidal radius is only a few hundred kilometers, close to the event horizon itself. This means tidal disruption events are relatively rare for stellar mass black holes. The star must pass extremely close, and most stars that get that close simply fall into the black hole more or less intact. Tidal disruption events are more common for intermediate mass and supermassive black holes, where the tidal radius is farther from the event horizon. But when a tidal disruption does occur, it's spectacular. The star is stretched into a long stream of gas. Part of the stream has enough energy to escape entirely. The rest falls back onto the black hole, forming an accretion disk and producing a bright flare of X-rays and ultraviolet radiation. These flares can last for months or years as the disrupted stellar material accretes. They're transient events, brief, bright phases in the black hole's otherwise quiet existence. Stage 8. Wandering the galaxy. Most of a stellar mass black hole's existence is spent simply moving through the galaxy. The black hole's initial motion, the kick it received during formation, combined with the gravitational pull of the galaxy, determines its orbit. Asymmetries during the supernova explosion can give the newly formed black hole a natal kick velocity of hundreds of kilometers per second, potentially sending it on a high-velocity orbit through the galaxy. Over billions of years, the black hole follows this orbit, making countless loops around the galactic center. It might pass through the galactic disk periodically, occasionally interacting gravitationally with stars and gas clouds, but mostly moving through the emptiness of space. The black hole's mass shields it from most environmental influences. Stellar winds and radiation pressure have negligible effect. Encounters with other stars are rare, given the vast distances between stars. During this long middle age, the black hole is essentially dormant. It's there,
invisibly warping space-time around it, but doing little else. For a black hole not actively accreting, there's no emission, no observational signature beyond its gravitational influence. This phase can last for billions or even trillions of years, the current age of the universe and far beyond.
Stage 8. The Far Future. Looking into the far future, the eventual fate of stellar mass black holes becomes speculative, dependent on cosmology and the ultimate fate of the universe. Current evidence suggests the universe will continue expanding forever, driven by dark energy. In this scenario, the universe grows increasingly cold and empty. Stars exhaust their fuel and die. Gas is depleted. Star formation ceases. Eventually, the universe consists primarily of dead stellar remnants, white dwarfs, neutron stars, black holes, separated by ever-growing distances. In this cold, dark future, black holes persist. They're among the most stable objects in the universe, impervious to time and entropy. But they're not completely eternal. Hawking radiation, discovered theoretically by Stephen Hawking in 1974, predicts that black holes slowly evaporate. The mechanism involves quantum effects near the event horizon, causing black holes to emit thermal radiation with a temperature inversely proportional to their mass. For stellar mass black holes, this Hawking temperature is incredibly small, around 10 to the negative 8 Kelvin for a 10 solar mass black hole, far colder than the cosmic microwave background, currently at 2.7 Kelvin. In today's universe, black holes absorb more radiation than they emit and actually grow slightly. But as the universe expands and cools, eventually the cosmic microwave background will redshift to temperatures below the Hawking temperature of even stellar mass black holes. At that point, black holes will begin net evaporation, slowly radiating away their mass. The timescale for evaporation is enormous. A 10 solar mass black hole has an evaporation time of roughly 10 to the 67 years, a 1 followed by 67 zeros. For comparison, the current age of the universe is about 10 to the 10 years. Black hole evaporation takes place on timescales that dwarf the current age of the universe by a factor of more than 10 to the 50. But in a universe that lasts forever, even these vast timescales eventually pass. Stage 9. Evaporation. As a black hole evaporates through Hawking radiation, its mass decreases, and as mass decreases, the Hawking temperature increases. Smaller black holes are hotter. For most of its evaporation lifetime, the Hawking radiation is extremely slow. The Hawking radiation is negligible, and the black hole changes imperceptibly over billions upon billions of years. But in the final stages, the process accelerates. When the black hole has shrunk to roughly the mass of a mountain, about 1 billion tons, its Hawking temperature reaches room temperature. It glows in the infrared like a warm object. As it continues to shrink, the temperature rises. At the mass of Mount Everest, it's thousands of degrees. At the mass of a large building, it's as hot as the sun's surface. At the mass of an aircraft carrier, it emits X-rays and gamma rays. The final moments are explosive. In the last second of its existence, the black hole releases energy equivalent to millions of nuclear bombs. In the last fraction of a second, it evaporates in a burst of high-energy radiation. And then it's gone. The black hole has completely evaporated. Its mass converted entirely to radiation and dispersed into the universe. What exactly happens at the very end, whether the black hole completely evaporates or leaves some Planck-scale remnant, remains uncertain. Our current theories break down at the Planck scale, and a complete theory of quantum gravity is needed to describe the final moments accurately. But in principle, Hawking radiation provides an endpoint to the black hole's existence. Nothing is truly eternal. Even black holes have a beginning and an end. The information paradox revisited. The evaporation of black holes raises one of the deepest puzzles in theoretical physics, the information paradox. When matter falls into a black hole, it carries information, the quantum states of all its particles.
If the black hole completely evaporates into thermal Hawking radiation, and if that radiation contains no information about what fell in, then the information is lost. But quantum mechanics says information cannot be destroyed. The evolution of quantum systems is unitary. Information is always preserved. This paradox has driven intense research for decades. Possible resolutions include 1. Information might be encoded in subtle correlations in the Hawking radiation. The radiation isn't perfectly thermal, but contains delicate quantum correlations that preserve information. Extracting this information would be extraordinarily difficult. You'd need essentially all the Hawking radiation and perform impossibly precise measurements. But in principle, information is preserved. 2. Information might remain encoded in the final remnant if complete evaporation doesn't occur. A Planck-scale remnant could encode all the information from everything that fell in, though how this works physically is unclear. 3. Our understanding of space-time at quantum scales might be fundamentally wrong. Perhaps the interior of a black hole is somehow connected to the exterior in ways we don't understand. Or perhaps space-time itself is emergent from more fundamental degrees of freedom that preserve information. The resolution of the information paradox remains an active area of research, connecting quantum mechanics, general relativity, thermodynamics, and quantum information theory.
Alternative endpoints. The Hawking evaporation scenario assumes the universe continues expanding forever, giving black holes the time needed to evaporate. But other cosmological scenarios suggest different fates. If dark energy changes over time, if its density increases rather than remaining constant, the universe could end in a big rip. Accelerating expansion eventually becomes so extreme that galaxies, stars, planets, and eventually atoms are torn apart. Black holes would be destroyed in this scenario, though not through evaporation, but through the fundamental instability of space-time itself. Alternatively, if dark energy decreases or reverses, the expansion could halt and reverse, leading to a big crunch. The universe would collapse back in on itself, with all matter, including black holes, eventually merging in a final singularity. There are also more exotic possibilities involving phase transitions of the vacuum, collisions with other universe bubbles, or cyclic cosmologies where universes are reborn from the collapse of previous universes. Each scenario implies different ultimate fates for black holes. But in most scenarios compatible with current observations, Hawking evaporation remains the expected endpoint for stellar mass black holes. Complete life cycle. Let's recap the complete life cycle. Stage 1, a massive star forms, burns brightly for a few million years, and builds up an iron core. Stage 2, the core collapses catastrophically. A supernova explosion ejects most of the star's mass, while the core collapses past its Schwarzschild radius. Stage 3, a stellar mass black hole forms, typically 5 to 15 solar masses, spinning rapidly and surrounded by debris. Stage 4, the black hole accretes nearby material. If in a binary system, it may accrete from a companion star, shining as an X-ray source. Stage 5, the black hole settles into a long middle age, orbiting through the galaxy for billions of years. If in a binary with another compact object, gravitational wave emission gradually shrinks the orbit toward eventual merger. Stage 6, occasionally close encounters with stars might produce tidal disruption events or brief episodes of accretion. Stage 7, the black hole wanders through the galaxy for trillions of years as the universe ages and grows cold. Stage 8, in the far future, once the cosmic microwave background cools below the black hole's Hawking temperature, evaporation begins, slowly at first, then accelerating. Stage 9, over timescales of 10 to the 67 years or more, the black hole completely evaporates in a final burst of radiation, ending its existence.
From stellar fire to quantum evaporation, from millions of solar luminosities to faint thermal radiation, from one of the most violent events in the universe to patient, eternal waiting. This is the life cycle of a stellar mass black hole. Observational evidence. How much of this life cycle have we actually observed? We've observed massive stars that are black hole progenitors. We've detected supernovae that likely produced black holes, though observing the moment of black hole formation itself remains challenging. The neutrino burst from a core collapse supernova like SN 1987A provides evidence of core collapse, though distinguishing whether a neutron star or black hole formed requires additional observations. We've detected dozens of stellar mass black holes in X-ray binary systems, observing their accretion processes and measuring their masses and spins. These observations confirm that stellar mass black holes with masses up to at least 20 solar masses exist and behave as general relativity predicts. We've detected black hole mergers through gravitational waves, observing the final seconds of binaries that evolved over billions of years. These detections confirm that black hole binary systems exist and merge, and they've revealed surprising details about black hole mass distributions and spins. We've observed X-ray transients and tidal disruption events, seeing black holes in their active, accreting phases. What we haven't observed is Hawking evaporation. The timescales are too long and the effect too weak for stellar mass black holes to be detectable with current or foreseeable technology. Hawking radiation remains a theoretical prediction, strongly motivated by thermodynamic arguments and quantum field theory in curved spacetime, but not yet directly confirmed by observation. Still, the overall life cycle picture is supported by a wealth of observational evidence at each stage where observations are possible. We're not just speculating, we're building on decades of observations across the electromagnetic spectrum and through gravitational waves. Closing. The life cycle of a stellar mass black hole is a story of extremes. It begins in nuclear fire, in the core of a star burning with the light of hundreds of thousands of suns. It's born in violence, in a supernova explosion that briefly outshines a galaxy. It lives through eons of quiet existence, warping space-time around it, occasionally flaring to life when matter falls into its grasp. And it ends, if our theories are correct, in the most patient fade imaginable, radiating away its mass particle by particle over timescales that make the current age of the universe seem like a brief moment. It's a life cycle that spans from the nuclear to the quantum, from stellar dynamics to gravitational waves, from thermodynamics to information theory. Understanding it requires insights from across physics. And it's a life cycle that connects to our own existence. The supernova that creates the black hole also disperses heavy elements into space. These elements become part of future generations of stars and planets. We exist because massive stars lived, died, and scattered their ashes to the cosmos. So when we study black holes, we're not just studying exotic objects at the extremes of physics. We're studying part of the great cosmic cycle of matter and energy that made our existence possible. Thank you for following this complete life cycle from beginning to end. If you found this journey valuable, subscribe for more comprehensive explorations of cosmic phenomena. And leave a comment. What stage of the black hole life cycle fascinates you most? Keep exploring, keep questioning, and keep wondering about the universe's most extraordinary objects.